let us first go over the proof of this sufficiency result and get a bit deeper. So what I showed before is correct, but I would like to go a bit deeper than the book shows, just to let you see how you can go if you want to the greater depth. So what I basically showed was a set of correct statements of the proof without unpacking them. So let us just remind that the proof of the statement was that if you have a game in this strategic form, then a sufficient condition to have at least one Nash equilibrium, but is for the set of Nash equilibria to be non-empty, is that for each player, the set of strategies of that player is a subset of some Euclidean space of a finite dimension Mi, some dimension for each player, and that space, strategy space, is the strategy set, is non-empty set. It's a compact set in the sense of Euclidean, and it's a convex set. I remind you that compactness is equivalent to saying that that it's closed and bounded, or it's equivalent also to saying in the Euclidean in finite dimensional Euclidean space, compactness is the same as closed and bounded, and it can be defined in several ways. I think that the general definition is that every cover of a set by open sets has a finite subset which also covers the set. But in the Euclidean case, it's equivalent to say that the set is closed, so every sequence in that set, if it converges to a point in that set, and bounded. So there is a large enough ball which includes that set. Now, convexity means that every 2 points, if you look at the straight segment between them, it has to be in the set too. Every 2 points in the set, that segment is also fully included in the set. So the second condition is that the preferences are continuous, and the third condition is that they are quasi-concave. Now, proof. So we show the basic idea. So that for every player, the preferences are continuous and the SI is compact. That's what we assume. Now, if you have a compact set of preferences a continuous set of preferences on a compact set, then the best exists and the maximum exists. And also, since the preferences are quasi-concave, then by definition, the BI, so the set of best responses of player I, is always convex. And that's exactly the definition. So the set of SI, which is there better than everything, which is there better, is always convex. And the next part is that since each preference relation is continuous, the graph of the function of best response or of the correspondence of best response is closed as a graph in the sense that we defined before. And from all those, the Kakutani theorem that we mentioned without proof before implies that there exists a point such that it belongs to its own B. Since B is a set valid function from S to itself. That fulfills all the Kakutani requirements, and S is compact, non-empty, and convex. Now, that is equivalent to being a Nash equilibrium. Being a best response to itself is equivalent to being a Nash equilibrium. Now, let us go over this proof and unpack some of the steps which we didn't go into depth. That's what I want to do now, in addition to what I did before. So, for every player and for every set of strategies for others, for all the others, the preference relation of the player is continuous, and the SI, the set of strategy space, is compact, and therefore we claim that the best response on S minus I is non-empty. Now, why? Simply because the utility function of player I, when I just given the strategies of the others, and when the utility function gets simply the strategy of player I, and returns the utility, the real utility, it's continuous because the preferences are continuous, and since SI is compact, so it's a continuous function defined in the compact space, and therefore it attains its maximum. That's a known theorem. Therefore, the best response by definition is the maximum, the maxima, and therefore it's not empty. Now, as I said, the quasi-concavity of the preference relation on this I is the same as saying that BI is the best response to anything is convex. As for continuity of, as for having the closed graph, it's proven in the following manner. So first of all, remember that the preferences of each player are continuous, and the continuity of a graph, that by definition means is that if you have sequences, any two sequences in the domain in S, so xn is the nth element of x and yn is the nth element of y, and every yn is in the B is the best response to xn, then by definition of the closed graph we need to prove that if the sequence Sn converges to x and sequence yn converges to y, both in S, x and y also in S, they need to show that not only that yn was always in the B of xn, but also the limit of yn, so y is in the B, is the best response to the limit of xn. So y is the B of x. That's what we need to show by definition of a closed graph, to show that it's a closed graph, that B has a closed graph. Now we need to show that from continuity and all that. So how do we do that? In order to show that y is in the B of x, we need to show that for every player, yi, the ith coordinate, is the best response, a best response to the strategies of the others in x, so to x minus I. So fix any such I, and now look at any zi in Si, and look at the constant sequence which is constantly zi. So every zin is simply the I, is simply a zi. It trivially converges to zi. Now, since for any I fix for any n, yn was preferred to zi because yn is a best response to is a best response to x minus I. So given that we fixed since yn, for any n, yn is the best response to xn, then for any n, yn of I is preferred to zn, in particular to zn. Then from the continuity of preference of I, also the limit y is preferred to again the limit of zn, zin is zi, because all zns are just a continuous sequence by definition. Now, since y is preferred to zi, and that's for any z in S, then yi is the best response. and that's what we need to prove, and we've shown it for any player, and therefore Y, the strategy profile Y, is a best response to the strategy profile X as required. And here we've proven everything for the Kakutani theorem, and then the theorem implies that there exists a fixed point in the sense that a point in S, X star, that belongs to its own best response, which is a best response to itself, and that's equivalent to that point being a Nash equilibrium. Okay, so that was just kind of, shall I say, an improvement on what we saw before, and an unpacking of several steps in the proof we mentioned before. And now let us go through what we saw, the theorem, the remarks, the example. And now let us talk about finite games, because we mentioned that finite games don't ever fulfill this theorem, because of course a finite set is never, of at least 2 points, is never convex, because there is nothing, the segment between them is infinite, so it cannot be fully in that set. So for finite set, we have actually the following interesting and classical statement, is that the mixed extension of a finite game always has a Nash equilibrium. That's the famous Nash theorem. And let us define the mixed extensions, which we defined already. But now let us define them again so that that sits well in your mind. So what about finite games? As I said, it's not necessary that a finite game, of course, has Nash equilibrium, for example, matching tennis, and then there are many, many other examples. But we define an actual extension, the mixed extension, where we are guaranteed to have at least one Nash equilibrium. And the intuition is probabilistic behavior. So let us first define what we mean by a distribution. So a distribution of a set X is defined as follows. So if a set is finite, the set of distributions are vectors, probability vector. Excuse me. The distribution over a set X is a probability vector which ascribes a probability, a non-negative real number for each element of the set X, and the sum of those elements is 1. So we ascribe a non-negative number to each element. The sum is 1, so each number can be interpreted as the probability of the set. It's indeed the probability measure on a finite set. Of course, we can speak about distributions on infinite sets too, but on a finite set, this is simply a set of non-negative numbers, which sum is 1. And we say that the distribution, again, is true for any set, not only for a finite set. It's simply that we can write the sum of it for a finite set. For an infinite set, we would need to talk about that more. Actually, for an infinite set, we can speak about the limit of this, series. And since they're non-negative, it does not depend by arguments, and does not depend on the order. And that's what we can say for an infinite countable set. If it's infinite, we would need to take the integral, and the back integral. That's gets technically gets technically complicated, but it's possible still to define much more general distributions, in the sense of distributions of a much more general set of a given set. That's the most general definition of a distribution. Yeah. So now we say also that for distribution, which can be seen as a function from x's to real numbers, non-negative real numbers, simply the function returns the probability of this element. We call the support of this distribution P to be all the elements of X which have a positive, strictly positive P. Now, in our world, of course, those who are not in support, exactly those who have 0, whose P is 0. Now, given this reminder of what is the probability distribution of a finite set, and as I said, we can speak about the probability distribution of any other set. Then now, given a strategic form game, we define a new game, which is called the mixed extension. That will always be infinite, uncountably infinite set. So, excuse me, game. So the strategy of any player will be of the continuum power. So 2 to the power Aleph 0, for those who know set theory. But anyway, it's infinite. And the mixed extension of a game is defined as the following. So it's a game denoted by delta. The strategies are simply the mixed strategies, all the distributions over the strategies of player 1, Cartesian multiplication with all the distribution over the strategies of player 2, and so on until all the distributions over the strategies of player n. So the new strategies, the mixed strategies are simply the distribution. And the strategy space in general is the Cartesian product of all the distributions of all the players. And the utilities are defined as expectations of the original utilities with respect to those distributions formally. One more thing is that so this Cartesian product basically decodes the probabilities are independent. They're called mixed strategies. And the original game, by the way, we can talk about dependent probabilities, and we are going to see this in this course. And that's much more complicated. Actually, it's less common to use, but most of the course we will use simply the mixed extension when the probabilities are assumed to be independent. And the original game is now called pure game. That's the game we are talking about, and that's what we are talking about when we don't qualify otherwise. And the strategies, again, that's the strategies we are talking about, are called pure. Now, the utility is the expected value is that integral of Lebesgue over the strategy, original strategy space, where the utility is weighted by the probability measure. And if the game is finite, then this Lebesgue integral is simply equal to the following sum. The sum over the set x of the utilities of x. So the utility of player I under the probability distribution P, as I said, is defined as the Lebesgue integral, which sums what player I get when the pure profile can be anything, but the probability of the profile is defined by the measure P, or by the probability distribution P, in other words, or it can be also the sum of the utilities of the player over all the profiles in S, and the utility of each such profile is weighted by the total probability of such profile to occur under P, which is simply the probability, the product, since it's independent, of probability of Si according to player I. So having defined this mixed extension, we just mentioned that the idea that we can look at the expected utility and that will actually matter. It's also something that we need the von Neumann-Morgenstern theorem for, which tells us that what actually players want is represented by the expectations of those linear utilities. So that's the mixed extension. And now let us briefly make two very simple observations. You can check at home, or maybe we will check them in the tutorial. First of all, this capital U, so the small u are the original utilities, capital U are the new utilities. This capital U, defined in a linear manner, as expected, it's multilinear. So what it means is that for any profile, strategy profile any mixed strategy profile, when I don't say it is pure, so any mixed strategy profile, and any mixed strategy profiles B and C for player I, any mixed strategies for player I, B and C, and any lambda between 0 and 1, the utility of player I when the others play what they do under the mixed strategy profile A. And player I mixes between B and C, so with a weight lambda and 1 minus lambda respectively. It's simply the mixing between the utility of the player gets when she plays only B against A minus I, and when she plays only C against A minus I, weighted with lambda and 1 minus lambda. So that's the multilinearity, and that simply immediately follows the definitions. And now for finite games, in other words, for games where the strategy space, the Cartesian product of its i's is finite, we can also say that for any strategy profile, mixed strategy profile in delta S, the utility of player I in that profile, again, that's natural because the utility of mixed utility is defined in this manner of linear combination. So it's kind of not surprising, but it's important to note that the utility of player I is the following linear combination of the utilities of player I when she plays the pure strategy, one of those pure strategies aside in her strategy set, against P minus I, the rest playing what they should play under under P. And that's weighted by the probability that Pi ascribes to Si. Now, what is E of Si? It's the unit vector of excuse me, that's the mixed strategy which we identify with the pure strategy Si. Because formally, capital U only gets mixed strategies. We don't give it Si as an input, we give it E of Si. It's a mixed strategy which has zero probability to the pure strategies other than Si. And 1 to Si. So it always does Si. That's the sense in which we identify the mixed extension with the normal game, with the original, game. And in that sense, we can say that going back, delta Si always includes equal to psi, and then the UI, they extend the original utility beyond those deterministic structures. And now, an important definition is that a mixed Nash equilibrium of a pure game, what is that? It's defined to be as a pure Nash equilibrium or just Nash equilibrium of the mixed extension of the game. So a game G has pure equilibrium. Moreover, it also has mixed equilibrium, which are defined as the pure equilibrium, which is the only thing we know till now, of the mixed extension, which we have just defined. Now identifying each strategy, each pure strategy, which the mixed strategy we just mentioned, in the set of the mixed strategies of psi, we claim that an equilibrium is pure if and only if the corresponding mixed strategy, so when each player plays this corresponding pure strategy with probability 1, is a mixed equilibrium. So every pure equilibrium is also a mixed equilibrium in the mixed game. Maybe there are other mixed equilibria, but every pure equilibrium is also a mixed equilibrium, and the proof is simple. So look at this E of Si, so at all those mixed strategies which correspond to those pure strategies Si. Now, if it's a mixed Nash equilibrium, then the conditions that nobody can deviate to any other mixed strategy are stronger than even stronger than what we need to have it pure, because even to a mixed strategy nobody can deviate. Definitely there is so stronger, so a fortiori nobody can deviate to a pure strategy. So those conditions imply the conditions required to say that S is a pure Nash equilibrium. Now conversely it's a bit harder, but not much. If S is a pure equilibrium, so now we assume that and we'll prove that, then the linearity of UI implies that if nobody can profitably deviate to another pure strategy, then nobody else can profitably deviate to a mixed strategy. Because if someone could deviate to a mixed strategy, then someone could find in that mixed strategy at least one pure strategy which is strictly bad, which is also a profitable deviation. So the mixed extension only can extend the set of equilibria. So the lemma claims that the set of equilibria, or the pure equilibrium, we don't qualify which is the pure equilibrium, is included in the pure equilibrium of the mixed extension, or by definition, it's included in the mixed equilibria. Now the question, of course, is that if the set of Nash equilibria is empty, can the set of the mixed equilibria be also empty? Or in other words, can the set of Nash equilibria of the mixed extension be empty? And the general answer is yes, but not if the game is finite. So if the game is finite, then the famous theorem of Nash from 1951, or in particular, which he got the Nobel Prize, every finite game always has at least one mixed Nash equilibrium. And now, before we prove it, let us mention several. I think I mentioned that in the previous lecture when we introduced a Nash equilibrium, mixed Nash equilibrium, but let me just explain them again for you. Several contended interpretations, so there is not really like an agreement which one is the correct one, or maybe which ones are the correct one. But it's nice to know them, at least some of them, most famous. So there are several contended interpretations what mixed strategies in general mean. So it can be an actual randomness that actually players decide that they were going to play randomly and then they just implement that. It can be that it's simply the steady state which players just notice stochastically. That's what they on average do. And then the optimum reply to a mixed equilibrium is also optimal against the historical frequency. So you just reply optimally against this. Your pure response can be different, but every pure response, so everything in the support of your mixed strategy of the mixed best response is always as best response. We are going to see it always has to happen. So this can represent a stochastically estimated steady state, and perhaps then that's even a result of a player representing all the population of players, and thereby it's even more reasonable that a player can play in different pure strategies as long as all of them are optimal given the strategies of the other. Another option, that's the mixed strategies, model pure strategies in a game which just is more complicated than what we see. So there is another game which actually is a better modeling of what happens in reality, and that has repercussions to the utilities. Now we just don't know or don't want to model or analyze that more complicated game. So we just simplify that by saying that assuming that players play those mixed strategies instead of explicitly modeling this more complicated game. Now another interpretation is a famous interpretation by Harsanyi. Really was a really famous game theorist. He had this notion and had this idea that since players can make mistakes, and definitely I cannot be sure that the others won't make a mistake. So the others won't deviate from whatever is opting for them. So assume that there can be path relevant, so random permutations, perturbations, excuse me, of the game. Now, then the mixed Nash equilibria can be shown, and Harsanyi showed that it's the limit of what actually happens in this permuted game when the perturbation sizes converge to zero. Now, the Bayesian equilibria, that's the generalization of a Nash equilibrium for games where you're not sure about what's going on. I won't go, of course, into details right now, but it's a very famous modeling, and that at least coincides with the intuition that nobody is perfect. And even if I'm not sure, even if I am sure that I won't make a mistake, I can never be sure that the others won't make a mistake. And what actually their utilities, maybe they don't even make a mistake in their rationalization, maybe they just perceive their utility differently. So that's a reasonable, at least definitely that an interesting interpretation. And the last one we mentioned, of course, you can think of any other interpretations, but the last one we mentioned, these are taken from the book by Osborne and Rubinstein. I do urge you, definitely recommend you you read that if you are interested. It's not something you have to know, but if you are interested, you are welcome to read that. Now, by the way, you see that there also they don't always agree on all those points. So since these are interpretations, these are not mathematical truths. Sometimes they have theorems like what Harsanyi proved, but in general, this is just interpretation. So there is a space for opinions here, because it's at best not an exact science already, at best something like economics or psychology, and maybe not in science at all when we just talk about what we mean and how it is reflected in life and all that. So definitely there is a space for disagreement, and I think that the argument that we see in the book within the authors is a nice example of constructive and polite argument in the places where there is a place for argument, like in the interpretation of otherwise proven result. So the last interpretation that I mentioned here is that the mixing can represent actually beliefs. So the beliefs is the probability I ascribe to the other person doing this or that, and the beliefs have to be consistent with common knowledge that everyone. The beliefs are common to everyone, and the beliefs are consistent with the fact that everyone knows that everyone is rational. So optimizes their utility given what they know. And the fact that it's common knowledge means that everyone is rational, everyone knows that everyone is rational, everyone knows that everyone knows that everyone is rational, and so on. Now, of course, this hierarchy of beliefs can be modeled, and that's not what we do now, but that's something which we can model. We're going to do it later in the course. But now, just see that it can be seen as beliefs. And then, of course, the predictive power is small, just beliefs about what player can do, if they are rational and they know that they are rational and so on, so then the predictive power about reality is not so large. Now, before we prove the theorem that every finite game has a mixed Nash equilibrium, let us now, excuse me, we give a simple proof, and then after some more deliberation, we give a maybe more insightful, so more down to earth proof. So the simple proof, or it's not so simple, it simply uses a very strong theorem. And the first proof is not what Nash presented, and it used because Nash used Breuer's theorem, and we use something else. Well, basically, eventually we do use Kakutani, which uses Breuer. Can be seen to be equivalent or generalizing Breuer. So we kind of use the same, we just don't see it. So proof is as follows. Why every finite game has a mixed Nash equilibrium. Now every player has the following. The set of the mixed strategies of the player is non-empty. It's convex, simplex on all the distributions are, of course, a convex set because those are non-negative numbers such that the sum is at most 1. It's compact because it can be shown that it's closed and compact, and excuse me, closed and bounded. Now the linearity of the utilities imply actually that UIs are quasi-concave and continuous with respect to the inputs, the probabilities, and therefore the existence theorem we proved implies, and we are done. Now it's simple, but simply it's because we've used the existence theorem, which, as I may remind you, uses the Kakutani theorem, which basically uses Breuer's fixed point theorem. So eventually it boils down to the theorem by Breuer, and so it's not so simple. Simply we have used some machinery which we already know. Now this proof, just please note, as it's needs finiteness. It's not even true without finiteness, but in general. But let's see where this is used finiteness. So you may just stop the video and think. Okay, so it uses finiteness. Otherwise, the compactness and the continuity, they don't necessarily hold. Now, what can be proven is that there are theorems which, under other requirements, prove the existence of mixed Nash equilibria for infinite games, but then they require other things like continuity of other. So I don't want to go there. These are not theorems for the basic course, I think. But for example, the theorem by Glicksberg and so on. You see, Glicksberg proved his theorem in 52, so only 1 year after Nash. So, an important, an insightful proposition, and that's the following. In a finite game, a mixed strategy profile is a mixed Nash equilibrium of a game. So in other words, it's a Nash equilibrium of the mixed extension. If and only if for every player and every pure strategy in the support of that player's strategy in P star is a best response to what the others do. So let's just make sense of that. It's very simple, or let's say it's reasonable, but let's just make sense. So a mixed strategy is a mixed Nash equilibrium if and only if every pure strategy in the support is a best response. So you only may mix between the best responses, and that's sufficient and necessary for that to be an Nash equilibrium. And that's very simple. So, by the way, one remark: you don't have to mix all the best responses. You just have to have that everything which you do mix is a best response. Now the proof is simple. Before we go to the proof, let me just remind you something important, that it supports the interpretation is that everyone's action are optimal against the historical sequence in the second interpretation. So the pure pure strategies which are in support of a mixed Nash equilibrium, they always has to be optimum themselves. That's an important thing. That's basically if and only if there is a Nash equilibrium. Now the proof is as follows. So assume that the profile, mixed profile P, is a mixed Nash equilibrium. It's a Nash equilibrium of the mixed strategy game, and assume that a pure strategy Si is in the support, but by contradiction, it's not the best response to what others do. Then take anything which is the best response, call it Ti. Now, intuitively speaking, bringing the weight of Si to Ti will strictly improve to, and that's contradiction. That's a contradiction. Formally, consider the mixed strategy Pi, which is the same as Pi prime, but the weights of Si and Ti have been varied. Si now, since it's not the best response, it does not get any weight. It gets 0. I mean, and Ti gets what it used to get plus the weight Si used to get. So we move all the weights from Si to Ti. Now, from the linearity, you have to be strictly better phi than Pi prime. That, of course, contradicts the assumption that P prime is an Nash equilibrium in the mixed extension. So we have derived the contradiction, and therefore a mixed strategy has to fulfill that everything pure which is in its support is a best response. Conversely, assume that everything, for every player, the pure strategy of that player in support is the best response. But to the contrary, assume that the there is some player such that the player does not best respond. So it's not, in other words, it's not Nash equilibrium. There is some player I such that it does not best respond. Then the linearity of the capital U implies that there exists a pure strategy in the support of the mixed strategy of player I, Pi, and some other pure strategy in the support of Pi prime. Okay, Pi is a best response, or at least it's better than Pi prime. So in reality, it means that there is something in Pi which is better than that corresponding player strategy in Pi prime. If nothing in Pi is better than nothing in Pi prime, then it cannot be that the linear combination is better. So it cannot be that the UI is strictly larger than UI of P prime. It cannot be that this happens. Now, from that player I derives more utility from Si than from Si prime, given that I just play P star minus I. We derive that actually Si prime is not a best response to P star minus n contradictory to the assumption. And we have proven the converse direction. Okay. So we have proven now the proposition, and now we are ready. Almost ready to the second proof of Nash theorem, but let us first draw an important corollary. Since a mixed equilibrium is characterized by every pure strategy in support being the best response, it means that every mixed equilibrium yields the same utility, or for every mixed equilibrium, every pure strategy in support yields that play the same utility. Or it yields the play the best possible utility, if only the strategy as I is played. And the next thing we are going to do is prove the Nash theorem. This is going to be directly using Brouwer's theorem.